Hello everyone. Today in the Neural Networks from Scratch series, we are going to introduce matrices in backpropagation. In the previous lectures on backpropagation, we looked at backpropagation through a neuron and backpropagation through an entire layer. So here are some of the notes from the previous lecture. As you can see, we did not use matrices even a single time, and as a result we had to write the partial derivative of loss with respect to weights for every single weight. Now imagine if we had a huge number of neurons, or if we had a huge number of layers, it would be very difficult and time consuming to write down the partial derivative for every single weight and every single bias, right? So it turns out that it's much more better and it's much more convenient to introduce matrices in backpropagation. Even in feed forward neural networks, when we look at the forward pass, unless we introduce matrices, it becomes really difficult to represent the forward pass because the neural network typically has a large number of neurons and a large number of layers. So the only knowledge which I'll assume here is the knowledge of transpose and the knowledge of multiplication of matrices. That's it. If you have not been through the previous lectures on backpropagation, it's totally fine. But this lecture you will appreciate just a lot more if you have been through the hard work which we put in the previous lectures. So let's get started with today's lecture. Like in the previous lecture, this is the neural network architecture which we are considering. We have basically four inputs: x1, x2, x3, and x4. And we are going to only look at one layer which has three neurons. The output of these neurons are Z1, Z2, and Z3. So Z1 will be W11X1 plus W12X2 plus W13X3 plus W14X4 plus B1, where the pink lines are the weights corresponding with the first neuron. Then this output of the neuron, which is Z1, is passed through a ReLU activation function, which leads to the output of A1. Similarly, for the second neuron, the weights are W21, W22, W23, W24, and the bias term is B2. The output of the second neuron is Z2, which is passed through the ReLU, which leads to A2. And very similarly, for the third neuron, the weights are W31, W32, W33, W34, and the bias is B3. So the output of the third neuron is Z3, which is passed through the ReLU activation function, which leads to an output of A3. Now, the output of each of these three neurons, A1, A2, and A3, is passed through another neuron whose weights are fixed to be 1. And the output of this neuron is A1 plus A2 plus A3. And then the loss is just calculated as A1 plus A2 plus A3, the whole square. So this is the neural network architecture which we have in this problem. And there are two things which I would like to point out here. First is the notation. Y is going to be A1 plus A2 plus A3, and the loss which we have L is just Y square, which is A1 plus A2 plus A3 whole square. As I mentioned in the last lecture also, it is very important to be consistent with the notation, so backpropagation becomes that much easier. Okay. So let's see, where do we introduce matrices in the first place. So for that, I'm going to be taking the first weight here. This is W11, W11. And if you want to find the partial derivative of the loss with respect to W11, you will first find the partial derivative of loss with respect to Y, multiply with the partial derivative of Y with respect to A1, multiply with the partial derivative of A1 with respect to Z1, and then finally multiply with the partial derivative of Z1 with respect to W11. That's why it's called as backpropagation, because there is a multiplication of four different terms with each other. So partial derivative of loss with respect to W11 is partial derivative of loss with respect to Y multiplied by partial derivative of Y with respect to A1 multiplied by partial derivative of A1 with respect to Z1 and multiplied by partial derivative of Z1 with respect to W11. Now for the sake of this lecture, I am going to take this entire quantity as partial derivative of L with respect to Z1. So then the partial derivative of loss with respect to W11 can just be partial derivative of loss with respect to Z1, which is this, multiplied by partial derivative of Z1 with respect to W11. And remember how Z1 depends on W11. Z1 is actually W11 x1 plus W12 x2 plus W13 x3 plus W14 x4 plus B1. So the partial derivative of Z1 with respect to W11 is just x1. So in this notation, the partial derivative of L with respect to W11 is just the product of the partial derivative of L with respect to Z1 multiplied by x1. And if you look at the partial derivative of L with respect to Z1, it will involve this derivative multiplied by this derivative multiplied by this derivative. So the weight does not come into the picture until this part at all. Similarly, we can write down partial derivative of loss with respect to W12, W13 and W14. So these are all the weights associated with the first neuron. So this is partial derivative of loss with respect to all weights associated with first neuron. They can be written like this. So let me change the color here a bit. So partial derivative of loss with respect to W12 can again be written as partial derivative of loss with respect to Z1 into x2. Remember, for all the weights belonging to the first neuron, this line, this pink line, this pink line and this pink line, all of them pass through Z1. So partial derivative of loss with respect to Z1, those will stay the same. So these three arrows, the first arrow multiplied by the second arrow multiplied by the third arrow will stay the same. The only thing which will change is that for W11, it will be multiplied by x1. For W12, which is this pink line, it will be multiplied by x2. For W13, it will be multiplied by x3. And for W14, it will be multiplied by x4. This is exactly what we have obtained over here. Partial derivative of loss with respect to W12 is partial derivative of loss with respect to Z1 multiplied by x2. For W13, it's multiplied by x3, and for W14, it's multiplied by x4. So these are all the partial derivatives of the weights with respect to first neuron, right? And similarly, there will be 4 entries for the second neuron and 4 entries for the third neuron, and there will be 3 entries for the bias. So there will be 15 entries, and I don't want to write this down every single time. So that's why we ask ourselves this question: what if all of these partial derivatives can be expressed in the format of a matrix notation? So I'm going to propose a matrix notation right now and then show you how it matches what we have already calculated. So the input x is a vector which has one row and it has 4 columns. So it is a 1 by 4. And then I'm going to define one more matrix which is DLDZ matrix or DLDZ matrix. This contains the partial derivative of loss with respect to Z1. It contains the partial derivative of loss with respect to Z2. And it contains the partial derivative of loss with respect to Z3. Remember, every neuron will have one output. So this is the first neuron. This is the second neuron. And this right here, that's the third neuron. Okay. So this matrix DLDZ is it has one row and it has 3 columns. So it's a 1 by 3 matrix. Now I'm going to take transpose of the input. So X transpose will be a column vector x1, x2, x3 and x4. It has 4 rows and it has one column. So it's a 4 by 1 matrix. And now I'm going to take the product of X transpose multiplied by DLDZ matrix or DLDZ matrix. So first let's check whether this product is even possible. Uh, for the product to be possible, the number of columns in the first matrix should be equal to the number of rows in the second matrix. And that is indeed the case. The number of columns in the first matrix is 1, the number of rows in the second matrix is 1. So we can proceed with this product. So to calculate the product, so it will be, so first let's see the dimension of the product. The dimension of the product will be given by the number of rows of the first matrix multiplied by the number of column. So it will be 4 by 3. So this resultant matrix is a 4 by 3 matrix. I want you to focus on the first column of the matrix, okay? So first let's calculate the first row and first column. For that I will multiply x1 with partial derivative of L with respect to z1. So this entry right here, first row, first column will be x1 multiplied by partial derivative of L with respect to z1. This second entry will be the second row multiplied by the first column. So it will be partial derivative. So it will be x2 multiplied by partial derivative of L with respect to z1. The third entry will be the third row here multiplied by the first column, which is x3 into partial derivative of L with respect to z1. And the fourth entry here will be the fourth row multiplied by the first column. So it will be x4 multiplied by the partial derivative of L with respect to z1. Now look at these quantities, this quantity, this one and this one. It is exactly similar to partial derivative of L with respect to W11, W12, W13 and W14. In fact, the first column of this matrix gives us the partial derivative of loss for the first neuron weights. So the first entry here gives us the partial derivative of loss with respect to W11. The second entry gives the partial derivative of loss with respect to W12. The third entry gives the partial derivative of loss with respect to W13. And the fourth entry gives the partial derivative of loss with respect to W14. Great. So the first column gives us the partial derivative of loss with respect to all the weights corresponding to the first neuron, which means all the weights which are shown in the pink lines over here. Now let's look at the second column. The second column will be, so x1, x2, x3, x4 will stay the same because we'll use the rows of these, but the product term will be partial derivative of L with respect to z2 instead of z1. So this will turn out to be partial derivative of L with respect to W21. This will be partial derivative of L with respect to W22. This will be W23 and this will be W24. So it turns out that the second column gives us the partial derivative of loss with respect to the second neuron weights, which means the partial derivative of loss with respect to all the neurons, all the weights which are shown in the green color here. And now finally, let's look at the third column. Again, x1, x2, x3, x4 stay the same, but we multiply by the third column of this, which is partial derivative of L with respect to z3. So then the first entry is partial derivative of L with respect to W31. The second is partial derivative of L with respect to W32. The third is W33 and fourth is W34. So it turns out that the third column gives us the partial derivative of loss with respect to the third neuron weights, which means it gives us the partial derivative of loss with respect to all weights shown in the orange color. So now I don't have to write this for the second neuron, third neuron and fourth, for the second neuron and third neuron. In just one matrix, which is a 4 by 3 matrix, I get the partial derivative with respect to all the weights. And then I can just use this matrix uh, when we perform the gradient descent. So when we perform the gradient descent, I will just use this matrix instead of trying to find values for every single weight. So that's the advantage of using matrices, right? Okay. So up till now we have seen about the partial derivative of loss with respect to all the weights. But what about the partial derivative of loss with respect to biases? So if you look at, let's look at the first bias, which is B1, which is the bias of the first neuron. It can actually be expressed like this. So partial derivative of loss with respect to the first bias will be equal to the product of partial derivative of loss with respect to z1 multiplied by partial derivative of z1 with respect to b1. Now let's look at this partial derivative of z1 with respect to b1. z1 is just this summation, right? So partial derivative of z1 with respect to b1 will always be equal to 1. So then this term will always be equal to 1. So then what will remain is just partial derivative of L with respect to Z1. So which we already have in this matrix, right? So the partial derivative with respect to the bias in this case will just be, so this is the partial derivative with respect to weights matrix, and the partial derivative of bias matrix will just be partial derivative with respect to Z1, partial derivative with respect to Z2, and partial derivative with respect to Z3. That's it. So this is the partial derivative of the loss with respect to the biases. So now we have a matrix which gives me the partial derivative of the loss with respect to all the 12 weights, and I have a matrix which is a one row and a 3 column matrix which gives me the partial derivative of loss with respect to the biases. So essentially I have all the quantities which I need to update the weights in the gradient descent. So now with just these two matrices, I have my parameter updates. That's the advantage of using matrices. So as a summary, what all we have learned up till now is that this formula X transpose multiplied by this DLDZ matrix gives us the partial derivative of loss with respect to all the weights. Let us actually cross check this with the previous example. So in the previous lesson, we took X, which is the input values to be 1, 2, 3, and 4. So the input values were 1, 2, 3, and 4. And we had taken the weight values and the bias values so that the partial derivative with respect to Z1 will be just 2y. And y in the first forward pass was equal to 21.6. That's how we had chosen the weights and the biases. So partial derivative of L with respect to Z, if you take that matrix for the example which we had considered, that is actually equal to 43.2, 43.2, and 43.2. You don't need to understand the previous lecture to follow here. For now, just keep in mind that X is 1, 2, 3, and 4, which are the inputs, and the DLDZ matrix is 43.2, 43.2, and 43.2. Why are there three entries here? Because we have three neurons, and every neuron will have a Z value associated with it, right? So that's why there are three values. So first value is for the first neuron, second is for the second neuron, and third is for the third neuron. So let's calculate this product X transpose times DL dz. Hopefully this will give us the same partial derivatives we obtained before. So these are the derivatives which you obtain here. So as I told you before, the first column gives us the derivatives of the first neuron weights. The second column gives us the derivatives of the second neuron weights. The third column gives us the derivative of the third neuron weights. Just keep these values in mind: 43, 86, 129, and 72. Let's compare it with what we had obtained previously. So in the previous lecture, let's look at the first neuron. The first neuron gradients were obtained as 43.2, 86.4, 129.6, and 172.8. These are exactly the same values which we obtained right now by using this formula X transpose DLDZ. So just by taking a product of two matrices, we obtained the same result as we obtained before. So we don't have to write down every single thing. Matrices actually makes our job much more easier. Now let's check for the biases. For the biases, we calculated that we just need to use the same matrix DLDZ matrix. So in this case, the bias values, the gradient of or the partial derivative of loss with respect to bias will just be 43.2, 43.2 and 43.2, because those are the DL DZ values. And let's check it with what we had obtained before. So before, if you look at the partial derivative of loss with respect to bias 1, it's 43.2. With respect to bias 2, it's 43.2. And with respect to bias 3, it's also 43.2. So we obtain the exact same values. That's amazing, which means the formulas which we had obtained for the matrices, they are actually working, and they have made our life significantly easier. In the previous lecture and in this lecture, we have not looked at the batch of input data, right? So only one input data is coming at one time. So in this particular case, only x1, x2, x3, x4 were coming, whose values were 1, 2, uh, 1, 2, 3, and 4. What if there was a multiple batch of data which was coming in, which typically happens in real life situations, right? If you want to make a cat and dog classifier based on input features, you have measurement data for multiple different samples. So there is usually a batch of data which comes in, and then the neural network has to make predictions for this batch of data. Remember that although multiple inputs come in, the weights essentially don't change for different inputs. There will be only one W11. There will be only one W11. There will be only one W12. There will be only one W13, only one W14, and only one B1. Similarly for all the other weights. Let us see how to implement backpropagation now if we have a batch of data. Okay. So I'm going to look at this input right now, which consists of three batches of data. The first batch is the first row, which is 1, 2, 3, and 2.5. The second batch is the second row, which is 2, 5, -1, and 2. The third batch is the third row, which is -1.5, 2.7, 3.3, and -0.8. Okay. And now let's look at the DLDZ values. For that, I would just need to draw the neural network once more. So these are the three neurons, right? And there are Z values coming from every neuron here. And actually input will be four different inputs. So let me mark the inputs with different colors. So this is the first input, second input, third input, and fourth input, right? This is x1, x2, x3, and x4. And then this is z1, this is z2, and this is z3. Now remember that for every batch of input which comes in, there will be a different z1, z2, and z3, which means that for, let's say, this batch, there will be one partial derivative of loss with respect to z1. There will be one partial derivative of loss with respect to z2, and there will be one partial derivative of loss with respect to z3 for this batch, and that's represented in the first row. However, remember that when a second batch comes in, there will be three other partial derivatives, and when a third batch comes in, there will be three other partial derivatives. So when you look at the DLDZ matrix, it will be a 3 by 3 matrix. The first row is for the first batch, second row is for the second batch, third row is for the third batch. Within a single row, the first column represents the output for the first neuron, which is DLDZ for the first neuron. Second column is for the second neuron, and third column is for the third neuron. The input matrix has three rows and it has four columns. Great. So now I want you to think of this. When we had only one batch of data which was incoming here, let's say only one batch of data, when we took the partial derivative with respect to, let's say this is W11. Let's say this is W11. When we took and this was X1, when we took the partial derivative of L with respect to W11, we multiplied partial derivative with respect to Z1 multiplied by X1, right? But now there are three different input data batches. So then what will be the partial derivative of the loss with respect to W11 since there are three batches? Uh, so the loss can be written as loss 1 plus loss 2 plus loss 3. Loss 1 is actually the loss from the first input data or the first batch. Loss 2 is the loss from the second batch, and loss 3 is the loss from the third batch. Now, if you find the partial derivative of loss with respect to W11, it will actually be the partial derivative of the first loss with respect to W11 plus the partial derivative of the second loss with respect to W11 plus the partial derivative of the third loss with respect to W11. So, if you look at this analogy here, we will again take the product of partial derivative with respect to Z1 multiplied by X1 for the first batch. For the second batch, we have to take the product of partial derivative with respect to Z1 multiplied by the different X. And remember, this partial derivative will also change because for each batch it is different. For the first batch it's 1, for the second batch it's 2, for the third batch it's 3. And then for the third batch, we'll take this product again, where we'll take the third batch input and multiply with the partial derivative in the third batch, which is different. And then we'll add these three together. Let me show how this looks like mathematically. For now, let's just focus only on the first batch. So partial derivative of loss with respect to W11 in the first input batch. So this will be partial derivative of loss with respect to Z11. So we are looking at the first batch, right? So we'll be looking at the first row. Um, and because we are looking at the first neuron right now, we are looking at the first neuron and we are looking at W11. So for the first batch, partial derivative with respect to W11 will be partial derivative with respect to Z11, which is this, multiplied by partial derivative of Z11 with respect to W11, which will be X11. So X11 is actually this. So the first batch, and we are looking at the first input, which is X1. That's why it's called as X11. Now we have to add to this partial derivative loss with respect to partial derivative of the second input batch loss with respect to W11. Now what is this partial derivative? It will be the partial derivative with respect to Z21. Now Z21 is this here. Remember, we are looking at the second batch and we are looking at the first neuron. So that's why we are looking at Z21. And then partial derivative of loss with respect to Z21 will be multiplied by partial derivative of Z21 with respect to W11. And that will be, remember, we are looking at the second batch and the first input. So that will be this. So that is also X21, which means the first column of the second row of X, which is this. And then to that we have to add partial derivative of the third input batch loss with W11, which is partial derivative of loss with respect to Z31, which is here. Since we are looking at the third batch and we are looking at the first neuron, multiplied by partial derivative of Z31 with respect to W11, which will be the third batch first input, which is this. So that will be X31. So the answer will be 1 into X11 plus 2 into X21 plus 3 into X31. So if you multiply this, you will get an answer of 0.5. Okay. Uh, to consolidate this further, let us do the same thing for partial derivative of loss with respect to W12. So here again, the partial derivative of loss with W12 is, so again remember, W12 is just, we are again looking at the first neuron, but we are looking at its connection to the second input, so W12. So it will be the summation of partial derivatives with the three input batch losses. So if we look at the first term here, which is partial derivative of the first input loss with respect to W12, it will be partial derivative of the loss with respect to Z11 multiplied by partial derivative of Z11 with respect to W12. Remember, partial derivative with respect to Z11 because we are still looking at the first batch and we are still looking at the first neuron. So although we are looking at W12, it still is corresponding to the first neuron. So we'll be taking the first row and first column from this DL DZ matrix. So that way this will be the 1 multiplied by partial derivative of Z11 with W12. So here we will be taking the second input from the first batch. So it will be the first row and second column from the input matrix. So then this will be equal to x12. Similarly, partial derivative of the second loss with respect to W12 will be equal to the partial derivative of the second loss with respect to Z21 multiplied by partial derivative of Z21 with W12. And partial derivative of the second loss with Z21 is, we are looking at the second batch and the first neuron. So it will be 2. So it will be 2 multiplied by partial derivative of Z21 with W12. So that will be, we are again looking at the second input but from the second batch. So it will be 5. So here we will be multiplying with x22 whose value will be equal to 5. And partial derivative of the third loss with respect to W12 will be partial derivative of the loss with respect to Z31 multiplied by the partial derivative of Z31 with respect to W12. And partial derivative of loss with respect to Z31 will be just, we are looking at the third batch and the first neuron. So it will be 3. So that's why this will be 3. And partial derivative of Z31 with W12 will be the partial derivative. Again, here we are looking at the second input, but we are looking at the third batch. So it will be the third row and second column. So it will be 2.7. So then this will be 2.7. 2.7 as has been also written here. So then if you add this up, this will be 1 into 2 plus 2 into 5 plus 3 into 2.7. So the value will be 20.1. Similarly, if you calculate the partial derivative of loss with respect to W13 and W14, they will be 10.9 and 4.1 respectively. I know this is a bit complicated to understand because just there are too many matrices and too many different labels. But if you write it on your own and if you always remember which input you are looking for and which neuron and which batch, you will be able to understand these calculations. Now, one more thing which I want to mention here is that currently we calculated partial derivative with respect to W11, W12, W13 and W14. Remember, the partial derivative of L with respect to Z matrix is such that uh, it is, there are same values for the second neuron and for the third neuron as well. So currently we only looked at first neuron, right? So we only considered the first column of this matrix, but the second column and the third column are the same. So all the partial derivatives which we calculated for the first neuron will be the same for the second neuron and the third neuron. So partial derivative of loss with respect to W11 will be equal to partial derivative with respect to W21 and 31. Similarly, partial derivative of loss with respect to W12 will be equal to partial derivative of loss with respect to W22 and W32. And partial derivative of loss will with W13 will be equal to partial derivative of loss with respect to W23 and 33. And partial derivative of loss with respect to W14 will be partial derivative with respect to W24 and 34. Okay. So that's how we will actually compute all of these 1, 2, 3, 12 partial derivatives. Now let's look at the bias. Since there are three input batches, the partial derivative of loss with respect to B1, which is the first bias, will be the partial derivative of the first loss with respect to B1 plus the partial derivative of the second loss with respect to B1 plus the partial derivative of third loss with respect to B1. And what is the partial derivative of the first loss with respect to B1? Partial derivative with respect to Z11 multiplied by partial derivative of Z11 with B1. So this is anyways 1. So this second multiplication will always be 1. So the answer is just going to be partial derivative of loss with respect to Z11 plus partial derivative of loss with respect to Z21 plus partial derivative of loss with respect to Z31. In other words, since we are looking at the first neuron, we will just look at the partial derivative loss with respect to z for the first neuron, which is 1, 2 and 3, and then add them up. So the answer will be 6. So partial derivative of loss with respect to b1 is 6, and with respect to b2 and b3 also it will be 6. So now we have calculated the partial derivative loss with respect to all the weights and all the biases, right? So if you put all of these together, we'll see that the weight gradient matrix is this and the bias gradient matrix is this. So the first column is the partial derivative loss with respect to the first neuron weights, which is W11, W12, W13 and W14. The second column is for the second neuron weights and the third column is for the third neuron weights. Similarly, if you look at the bias gradient matrix, we already calculated it to be 6. So it will be 6, 6 and 6 for the 3 neurons. Now, we put so much effort to manually understand each of these computations and to find these partial derivatives for the batch of data, for the weights and the biases, right? Let's now just use the same formula which we discussed before. And that formula is x transpose multiplied by dl dz. And let's try to see whether we get a similar answer. So x was already defined over here. X was already defined over here. We just take the transpose of x and we multiply with the dl dz matrix which was already defined. So if you do this calculation, you will get the final matrix as 0.5, 20.1, 10.9, 4.1, and these columns will be repeated. And if you see, this is exactly the same matrix which we obtained through our manual calculations. This is again to demonstrate to you that if I could have directly told you this formula, but then you would have appreciated it much less than looking right now, where if you did not know this formula, you have to put in so much effort for computing these values manually, right? So that's the beauty of using matrices even for back propagation. So these are the partial derivative with respect to the weights, and for the partial derivatives with respect to the bias, we just sum the different rows. So you sum the first row, the second row and the third row. So that's why you get 6, 6 and 6, which was exactly the same thing which we obtained when we did it manually, 6, 6 and 6. When we look at the Python code in the next lecture, you will see that for bias gradients, we do this np.sum dl dz axis equal to 0, which means that you just do the summation across the rows. And when you see this, you should again realize that we have already done this here. It just means adding 1 plus 2 plus 3. So 6, and then for the second column and for the third column. So finally, in this lecture, we have demonstrated that for a single batch of data and even for multiple batch of data, this formula, which is x transpose multiplied by dl dz, works for all. So even if you have a batch of 100,000 data points which are inputted to the neural network, it will be so tedious to do every single thing like we did here, right? But you don't need to do this. You just need to take the product of two matrices. That's it. And for bias, the calculation is similar. You just look at the DL DZ matrix and just do the sum along the rows, or you sum the different rows. That's it. So we'll be looking at Python coding in the next lecture. But to really appreciate it, I wanted you to appreciate how matrices really come into the picture and what is the significance of this formula um, X transpose DL DZ. So thank you so much everyone. I hope you have started to realize why matrices are so important in neural networks. And if you understand that, life just becomes much easier. But you will not understand it if you just listen to videos. You need to write it down on a piece of paper similar to what I'm doing right now. Thank you so much everyone. I hope you are deriving value from these lectures. I'll see you in the next lecture.